but let me finish this first. So as I was saying, we need to finish the plotting of this, sketching the plot. It is a very rough sketch, as you have seen. To finish the sketch of this curve, we already have 1 point on it, and we also have 2 holes in the domain. So the first comes from according to this picture over here, the x-intercepts come from the roots of the numerator. So numerator is a polynomial, and we deal with it just like we have been. Okay, so find its zero, its roots, and that gives us the x-intercepts of our rational function. And then we do the same with the denominator, and then also factor it and find its roots. Okay, so that's the denominator x minus 1, x plus 1, and that gives us those holes. The holes also give us those vertical asymptotes. So the asymptotes, we don't care about them a lot, just every time you actually plot them, not by hand but with anything, graphic calculator, you see those vertical lines. Okay, how the graph approaches them, you can see it right here. And so just worthwhile to know the word that describes that behavior, asymptotic behavior. But here we are after a rough sketch, and all we need to do is just to figure out the signs of where the function is relative to the x-axis, because this is y is positive here, and y is negative there. Okay, relative to, this is the x-axis, and then the graph in part lies above and in part below the x-axis, and so then we'll know, if we know the sign of y over here, then we'll know where the graph lies, roughly speaking. Okay, that's not too complicated. We just look at the factors, and we don't have too many factors. We have 4 factors, so let's just list the factors, and the factors are x, 3x squared plus 1, x minus 1, x plus 1. Okay, and then there are these 3 points where there might be a change of the sign of these factors. Okay, so x, what do we know about x? It is a function. All of these are polynomials. We know there's everything there is to know about them. So it starts, it's x, graph like this. It starts negative. It hits 0 at 0, and then it becomes positive. Okay, so that's simple. Okay. 3x squared plus 1. What do we know about the sign of 3x squared plus 1? First of all, why didn't I factor it? It is irreducible, right? And what's so special about irreducible? They cannot be factored, which means that they do not cross, they don't have x-intercepts, which means that they are either lie entirely below or entirely above the x-axis, which means in this particular case, what is it? Above or below? Above, right. So 3x squared plus 1 always will be positive, never 0, it's certainly never negative. Okay, so which means that this thing does not really contribute anything to what we have been, what we want to do here, because we're interested in the signs, and the sign is positive. One of the factors is always positive, so it does not change the sign. The x will not affect that part. Okay, x minus 1, it starts negative, and then it hits 0 at 1, and then becomes positive. Okay, all right. The last one, x plus 1 hits 0, starts negative, hits 0 at negative 1. Okay, these are the three values of x that we're interested in, where things happen. Okay, so and these are the ones that we are looking at. Okay, so hits 0 and then becomes positive. So the factors are, when we're listed, we already have finished with factoring So either we'll have linear factors, so they will behave like those three, or they're irreducible quadratic factors, and they will not contribute anything. You just need to know for sure whether it's positive or negative. Okay, so and then we put them together like a line, because now f multiplies these two and then divides by those two. But as far as sign is concerned, it doesn't matter. You multiply by a negative number, or you multiply or divide by a negative number. The answer will be the opposite. Okay, it doesn't matter whatsoever. So then I'm looking at these intervals once again, one at a time. So this is where it's happening. This is my big table. Okay, and then I just look one interval at a time. I have 4 intervals. 3 points separate the x-axis into 4 intervals. And if I look at the first interval up to -1, I go down and I have negative, positive, negative, negative. Right? You see those minus, then plus, then, well, I can just ignore the second one. I have 3 minuses. I have 3 minuses, and altogether it gives me what? Negative, 3 negative numbers divided or multiplied by each other. What's the result? No, it's negative, 3.
Oh, okay, yes.
Yeah. 3 negative gives me negative. And, well, that's it. That's it. Moving on to the next one. I have now 2 negative, and the third is positive. Now, this one is positive, right? And this one is 0. Actually, it's not 0, but rather it is a hole in the domain. So I'll try to make a circle that does not look like a 0. Okay, so that's not a 0. It's a hole in the domain. Okay, and same here. Okay, so as we pass through 0 on the x-axis, the third column over there, I have plus, plus, minus, minus, and it will be negative. So only one negative number there is positive. And on the right, these are positive. Okay, so altogether, I have my signs as planned, and I can roughly plot the graph of the function now. Okay, so I have a hole. Okay, so these are my asymptotes, or rather, that's where the graph does not cross. And then the function is negative, negative. Well, let's just say. I'm going to use a marker to emphasize the point that we don't know roughly what it looks like, just so very roughly. But it's negative. Okay, so it's negative, and it does not pass through the asymptote. Okay, then in the middle, what's happening? It is positive, and then it hits 0 here, and then becomes negative. Right. So if I look at the 2 intervals between -1 and 1. Or this big interval, then you can see it's plus, 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 0, minus, minus, minus. So 0 over here, minus, minus, minus. So which means that my graph roughly goes like this. So once again, it has to be positive, and it cannot get through the asymptote. Okay. On the left, it's negative, does not pass through the asymptote, so it climbs down at all times. And then past 1, we have a positive function. So once again, I'm just using a marker, so a lot of stuff might still be happening, but we don't care, because our interest is really a very rough sketch of the picture of the graph. And then this is it. So there are more subtle things that we might worry about in the future, but right now all the tools that we've got are these signs as well as asymptotes, and we have our answer. So that's a skill that's also necessary to once the polynomial or rational function is factored, you should be able to sketch the graph in this manner. The easiest way, I think, so we had 2 actual approaches. One was based originally on the multiplicities of factors. Remember, when multiplicity is even, we touch the x-axis. When multiplicity is odd, a multiplicity is odd, we are jumping all over it. Or this one, I think this is the simplest one. You just list the factors. They're either linear or reducible quadratic, and the signs of their is absolutely clear where they're positive, where they're negative, because they're linear factors. And then just go vertically to find out the signs of f at every single location. That gives you the sketch, a pretty good sketch that you can imagine. There is algebra behind it. Why such a rough sketch still has a value, we have solved one equation, which is, what's the equation? Is f of x equals 0. Okay, so this is what this analysis and this rough sketch gives us. It gives us certain algebraic, the ability to solve certain algebraic problems. Number one is the easy one. It is an equation. In equation, you just take your function, set it equal to 0, and what do you produce? Of course, the x-intercepts. So we have done this already many times. So I'm not gonna. I emphasize in this particular case we have only one x-intercept. But there is more. There are also several inequalities. And that's another thing that also skill that is useful, is the ability to solve a polynomial and rational inequalities. So in this particular case, what I'm talking about is I take my function x 3x squared plus 1 over x minus 1x plus 1, and to begin with, maybe I need to solve this inequality. That's number one inequality that you might solve. Number two, less than 0. Number 4, larger than or equal to 0. Number 3, less than or equal to 0. So simultaneously, this part, it solves all three. It solves, or in fact, all 5. The equation and the 3 and the 4 inequalities are hidden right in that. It is a summary. What I circled there is the summary of solution of these 4 inequalities, and all you have to do is just to read the answers from that rows of minus and pluses. Let me start with the x-intercepts, or rather with the equation. So let me erase this. Okay, so number 1 is x 3x squared plus 1, x minus 1x plus 1 equal to 0. Okay, this solution set, which is what I'm interested in right now, is the x. What's the solution set? So I will be listing here solution sets. So looking at what is circled there, what is the answer for my equation? What values of x will make my fraction equal to 0? It's all there, so just look at it and you'll know the answer. So I don't want you to actually try to solve it again. We already have solved it. I just want you to see that it's right there. So what's the answer?
0.
0 and 0 only, right? So the picture, as you can see, once again, let me make sure that there is no confusion here. So the values of f over here are written, and wherever you have those circles, let me once again do it. These are holes. Holes. So we do not take them as the answers or for anything. We in fact will have to exclude them. Okay, now positive values. Where is it positive? It is where we have pluses. We have pluses, so it will be what negative 1, 0, union 1, infinity. Okay, that's where the pluses are. So I'm just reading the intros. I guess what I circled is I didn't circle the the part on the x-axis isn't there. So this is actually -1. These are x's over here, -1, 0, and 1. Okay. So x is in the first row, and then y's in the second row. Okay. So once again, when x is equal to 0, we have 0, and that's the only possibility for 0. But the positive numbers are wherever our pluses are marked, and that will be between -1 and 0, and then for 1 to infinity. Less than 0, what's less than 0? For the second inequality, what's the answer? Yeah, I want intro notation, I guess. So it's negative infinity, -1. Is that it? And 0, 1. Okay. Okay, so now larger than or equal to 0. Larger than or equal to 0, what's the difference? So larger than or equal to 0, which means that we include this. We have to include 0 as a possibility. That's all. So that's easy. So I take the first inequality and add 0 to it. So it will be -1. -1 does not include it because the function is undefined there. And 0 included. See the bracket. Okay. And then once again, the 1 is still excluded because of the same reason. 1 plus infinity. So bracket for 0. And brace in the parentheses, round parentheses for -1 and 1. And for the opposite inequality, I take the second inequality solution, this solution set for the second inequality, and add 0 again. So it will be negative infinity and -1 union 0 included 1. Okay. So it feeds both ways. The algebra, we derive some algebraic results from the geometry that we have established, and conversely, if you have solved the inequality ahead of time, you could roughly already sketch the graph. You can see the difference from maybe equations or inequality you've seen before is we push, for this to be applicable, we push everything to the left-hand side so that there's only 0 on the right-hand side. And then this method will be applicable. Otherwise, you will be comparing two functions, which is much more complicated. Okay, so that is it for the rational functions for now. And so there will be more algebra. But before, there is one more topic, which is not algebraic entirely, but more geometric, that we faced before, and that's even and odd functions. So let's start with the y, even and odd, and they're similar in some sense, similar to even powers, and respectively to odd powers. So you might remember that, say, x squared looks like this, a parabola, and then x squared, while x fourth, it looks similar except kind of flatter at the bottom. Okay, and similarly, if we have we look at odd powers, I look at x cubed and x fifth, x cubed, x fifth. They look quite a bit different. Let me correct myself slightly. Okay, so the similar, in what way similar? The graph looks somewhat, the graphs don't have to look similar, they have, the similarity is in terms of symmetry. Not general look, but in terms of symmetry. So do you remember the symmetries, or the symmetries that we're facing? What kind of symmetries these are? Yes, you have to be specific. In which one, in which symmetry, and which of the two has it.
X squared and x to the fourth.
Yeah. So these have mirror symmetry. About we have two. Well, the function can only have one symmetry. It is about the y-axis. About the y-axis. You cannot have a symmetry about the x-axis unless it is a zero function to begin with. So the x-axis, the only function that y equals 0, the only function that has this kind of symmetry that you flip it about the x-axis and you have the same function. But these are flippable about the y-axis. Okay. What about the odd powers? What kind of symmetry is this? Rotational, specifically, it's 180 degrees rotation. So we could rotate a plane in any degree that we can imagine, and there could be. I'm not sure if it is actually possible to have a symmetry of that kind. If you rotate 90 degrees, can you have a function that rotate into itself under 90 degrees? I don't know. Anyway, this is 180 degree rotation, but the better expression is central symmetry, I think. Slightly more specific. Central symmetry with the center being the origin. So it's a good idea to remember that it is indeed a rotation like this, 180 degrees around the origin. But another one is to see how you pass from every point to another point on the other end through the symmetry like this. So this is the mirror symmetry. You pass through the y-axis from left to right. Okay. Same distance, you pass under 90 degrees, and you measure the same distance that you traveled on the other side of the y-axis. Okay, so that's your mirror symmetry about the y-axis. Central symmetry is the same story, only you pass through this origin. Okay, so that's the central versus I don't know, axial maybe. I'm not sure what the good word to be here. So the symmetry about an axis or a line, or symmetry about a point. So central symmetry is also quite descriptive, even though physically it is easier to actually execute rotation to get the function into itself. So that's how we describe odd and even functions. So even functions have this symmetry. And odd functions have this symmetry. We still haven't defined that, but we'll do it in a minute. Odd functions have this symmetry. Well, let me quickly have a couple of examples, at least, that are functions that have the symmetry without but not without the power function. The easiest one is just to vertical shift. For the first one, you have a vertical shift which will not change the symmetry about the y-axis. Okay, so it still has the same property. Okay, so shift up or down, vertical shift of any power function, or any function that is already even, will produce another even function. Okay, what operation could I do, if you can see, what can I do with those two on the right that would keep them still odd? You see, if I take that function on the right, and shift it up, it won't be odd anymore. It will lose the symmetry because it will be moved away from the origin, and that one thing is you definitely want to have your function to pass through the origin in order for it to be odd. So what can we do in order to preserve this property? You still will move away from the origin, I'm afraid.
Is it a stretch?
A stretch. A vertical or horizontal stretch will preserve that. So in fact, maybe let's make it very sharp like this. So vertical stretch. Okay, so this is all good, but our interest is algebra. We know how to describe these transformations algebraically. So if you remember that these transformations xy goes to under this flip about the y-axis. Where does xy go? It's right here. This is my flip. Goes across horizontally. So it's a horizontal flip, which means what happens to y? Nothing happens to y. And what happens to x? It flips. It flips the sign. So negative x, y. Okay, so that's the transformation. And for odd, look at, once again, the central symmetry idea is better because you can see how we're going across. This point ends up over there. So not only something happens to x, in fact, the same thing happens to x, or something happens to y too. So what is it? Well, you think about it, this point is 1, 1. What's this point? The opposite. They both become negative, yeah. So negative x, negative 1. You don't say, yeah, so 1 and negative 1 both became negative. You don't say that necessarily xy become negative. They may have been negative to begin with. You multiply by negative 1, which means that positive becomes negative, negative becomes positive. Okay? So with that, well, here's a, let me have maybe an example. An example that we're going to deal with anyway, and that's a circle. Remember the formula of a circle? X squared plus y squared is equal to 1, centered at the origin. Okay? And this circle, not a function, has both of these symmetries, as a matter of fact. So you can run across the y-axis like this, and you still, at your point, wherever you start, will still end up on the circle. Or you can run across the center, and once again, the point, whichever point you pick, it will still end up on the circle. Okay, so circle has both, but it is not a function. It is a relation. So it might have more symmetries than a function. So our interest is now what is the formula, or algebraic restriction. Algebraic requirement. And here what it is, f of negative x is equal to f of x. Okay, that for a function to be even, this is what the equation has to satisfy. If you look at this, you'll see y, right? So as you can see, the transformation makes x flip its sign, but does not change y. Okay, so a point, if we're starting point here is like this. This is f of x over here, and this is x, and this is negative x. Okay, and then one point flips over to the next location, and it's supposed to produce the same y. Okay, so as you can see, for these points presumably they are on the graph of the function, which means that they correspond to the value of y on the y-axis. And if I start on the right, if I start with x, I end up with f of x, right? But if I start with negative x, I end up with f of negative x. They just happen they would have to be equal to each other in order for the symmetry to be satisfied. Okay, so if the second point is higher, which actually looks higher, if the second point on the left is higher than the one on the right, then there is a misalignment, and the function, the f of negative x is larger, and they are not equal to each other, and there is no symmetry. But with symmetry, they have the same distance. If you start with two values on the left and the right, the same distance, then the height should be the same. Okay. So with that, I give another example. A very important one, and that's the absolute value. F of x is equal to absolute value of x. You can certainly probably let me put it aside for a moment. Let's quickly confirm the x squared satisfies this. The simplest example where everything comes from. So what do? I plug in negative x into my formula. So f of negative x is equal to negative x squared, which is negative x, which is equal to x squared. So it confirms. X squared is equal to f of x. So we start with f of negative x, use our specific formula, and we're supposed to end up with the same formula as in the beginning, which I did, because negative x disappears under square. Okay, if I take fourth power, the same thing will happen. But the absolute value is also an interesting example. It is certainly not a power function, but it works out exactly the same way. If I plug in negative x, then we know that that's what we know about what absolute value does by design. It cancels out the negative sign, if any. Okay, so then the absolute value of x is the same as the absolute value of negative x, and so once again it checks out. Okay. So there will be more examples, but at this time these two is enough. I just want to go back and do it side by side. I want to do it with odd functions. So I'll be looking at this expression, and once again I want an algebraic requirement. But as you can see here, we flip both x and y, so my requirement becomes f of negative x is equal to negative f of x. That's the algebraic requirement. So if for even function, it's very different, right? If for an even function we flip x, nothing happens to y. For the second one, if we flip x, y flips too. Okay. Well, you can see the graphs look very different, except for the circle. So these are certainly very different looking graphs. Okay. So I do have a picture here. So if this is x, I flip it to negative x. Then the end result should. That's a terrible graph. X, this is negative x, this is f of x, and then and this is negative f of x, or rather, this is f of negative x. Okay, so once again, if this point is on the graph, then x goes to f of x in that manner. If this point is on the graph, this negative x goes to f of negative x under f in that manner. And then from the symmetry, we know that this is these y's, this y and that y, that have to have the opposite signs in order for the function to be odd. Okay. So example, let me do x cubed. An easier substitute for the formula frequently is f, what is it? Negative f of negative x is equal to f of x. Okay, so just pull negative to the other side, and so negative and negative are supposed to cancel each other somehow in this procedure. So yeah, let me take x cubed. F of x is equal to x cubed. So I go to verify. I write f of negative x is equal to negative x cubed. Okay. and then, well, I take a negative sign here. Okay, negative. Okay, so it is then negative, negative 1 cubed, x cubed, and I end up with x cubed, which is f of x. So it checks out. So, so the functions usually are fairly simple, and then just plain algebra of cancellation of those negative signs will give you the answer. So there is no good example of what we have seen so far, a function that is as simple as absolute value of x. Well, let me do something else, and that is, how about I try the second definition applied to x squared. So x squared has been proven to be even on the left, example 1 on the left. Now, how do I know? Maybe it's odd too. So let's show that it's not going to work out. So f of x is equal to x squared. I take negative f of negative x and substitute these into my formula in order to verify. So I have negative x squared, right? And then I already know what's going to happen. It's going to be half negative x squared. Okay, so so not the same as x squared. So what we're talking about here, not to be confused with equations, we are talking about functions equal to each other. So when do two functions equal to each other? How do you make sure that two functions are equal to each other? You have two different formulas, and then you're thinking maybe it's the same power function. How do you find out? That's well, you mean the function produces correspondence, right? So you input output. So yes, then the output should be the same as long as the input is the same. So even though the formulas are different, when you plug in the same value, you will know that you get the same output. So if you can verify for every single value of x, you know it's the same function. If there's only one mismatch, it's not the same function. Okay, so this is the simplest case when you have a formula. Then if two formulas cannot be converted one into the other through some algebra, then you know that their function is not the same. So which is what I'm talking about is x squared and negative x squared. You see, they are equal to each other when x is equal to 0. So it's not like there are no overlap. There is one point they do have. These two functions have one value in common, but the rest of them are not. So that's why we say these are not the same functions, and that is why the condition is not satisfied. So to make that clear, I guess I should just say here, for all x. For all x. So for all x in the domain of f, this has to be satisfied. Okay? So if we demonstrated that it fails just for one value, so this one fails for x equal, how about, doesn't matter which one, x equal 1, as long as it's not 0, the condition fails, and so this function, x squared, so y equal x squared is not odd. In fact, it is to be expected, a function, if you pick a function at random, it's not going to be either odd or even. It is a nice, very nice, two nice classes of functions that are have symmetries, and functions generally, if you take one at random, they're not going to have any symmetries. Okay, so just a few more examples maybe of this, of odd and even functions from what we have seen. Powers, but also the reciprocal powers also have the same, or rather not reciprocals. The reciprocals of the powers have the same symmetry. So instead of having having x squared and x cubed, x fourth, x fifth, I'll take the reciprocal of those, which is what we've just been talking about. These are all rational functions. Well, in fact, I could take 1/x. So this is 1/x. Looks like this. 1/x cubed looks pretty much similar, only it runs faster. So it becomes closer to the asymptote much faster, but otherwise it's similar. 1/x squared will look like this. The same idea, only the function remains positive at all times. Okay, and in addition, it also makes it odd. And the 1/x, well, maybe not like this, 1/x to the fourth has this more extreme behavior as far as asymptote is concerned. So once again, these are even, and these are odd. So like I said, if you start with an odd function and do something with it, such as take the reciprocal, you have a chance that you're going to end up with a function that is still odd. Same with even. Other operations, not necessarily. So adding numbers will make it shift vertically, and so the function will not be odd anymore. Horizontal shifts definitely also will ruin that. Vertical stretching works with both of them. Vertical stretch will preserve evenness as well as oddness. But the examples taking the inverse, that's the most problematic of that, as you can see, as x squared. So another example, if I start with my x squared, the trouble is the x squared, it's not 1-to-1. So it means that when we take the inverse, it's not going to be, you have to first cut the half off of the graph. So this one, x squared, 1-to-1. Then you go on and get the inverse. But once you cut half of it, then you are really not, you don't have a chance of having a function being odd or even. On the other hand, but if you take x cubed, that's different because you don't have to make that operation. X cubed is flipped, so this is x cubed. You flip, remember you flip it about the diagonal in this diagonal. Oops. Y equal x, flip. So we did flip here, but first we had to cut, and this one we go straight to flip because it is 1-to-1. Okay, and so the end result is immediately its inverse, cubic root. Of x. Okay, and it is once again what's good about it? Yes, it is 1-to-1. Yes, but that's not what I'm asking about. The symmetry. The symmetry. What's the symmetry of the second function? Well, this one is odd, and this one is still odd. Yeah. The same symmetry as the original one, because think about it. You flip a piece of paper, and something is drawn on the paper. If that object had a symmetry, then it still has that same symmetry. Okay. So indeed, if the first function, what the symmetry was the central symmetry. After we flip it, it still has that central symmetry. So if the function originally was odd, it remains odd after that flip. Another related problem, or how you can encounter the issues is like this. Let me make a plot here. Okay, the question would be, suppose this is a half. Suppose this is a half of an odd function, or it is a half of an even function. What are you doing? And you're supposed to plot the rest of it. So how do you plot the rest of the graph? Yeah, so that's right. So you just take that graph that you have, flip it, and then attach it. Okay, so I don't think I have that with this. Let me do it by hand. Okay, so I'm trying to do it by hand. So I'm flipping it, and then I'm trying to reproduce the same behavior. Close enough, I think. Okay, so as you can see, you can confirm, does it have this mirror symmetry? It does, right? What about the other one? So the idea is the same. So you copy the piece that you do have, and then flip it, and then attach it, if you can. So can you attach it, really? So this same shape, where is it going to be? Where is the location of the second branch? On the opposite side of the origin. It goes diagonally. Okay, so it will be here somewhere. So where does it start? Right. So like you start on the y-axis, going in the opposite direction, in the same upside down in the opposite direction. So that's a central symmetry for you. Okay, so if in any doubt, so that's how you do it in one sweep. But you can try to do, if in any doubt, do it point by point. So pick a point, find a counterpart like this, and if you do enough points in that manner, you will find the rest of them. It's really not that bad. Sometimes you need like 3 or 5 points, and you're fine. Okay, so that's all.